Alright, so in this page we have shown you how to do the two-parse algorithm based on hashing for the join, right? And we can see we have 3 steps. We can do the partition of relation S first and relation R, and then we can join them together. So in the next page, we also have a diagram of the framework to show you how this method or this algorithm works. So given the relation and relation S, we do the partition first, and then we do the joins, right? So for the partition, it will be, very similar to the framework we showed before, right? Given a relation, we can partition all the tuples or the blocks inside it into some buckets. So we can partition both relation R and relation S according to a hash function, right? This hash function will decide based on the shared attributes between relation R and relation S, or the join attributes, right? If they have the same join attributes, it will assign the tuples to the same buckets. So the tuples in both relation R and relation S will be assigned with the same partition ID or the bucket ID if they have the same join attributes or the shared attributes, right? So this is to the partition according to the algorithm we showed before. So the hash function will be shared between them for the partition of both R and S. In this way, we can ensure all the bucket numbers in these two relations will be the same, and also for the tuple with the same join attributes, they will be assigned or mapped to the same buckets. So based on the partition results, we can have the result as shown here, right? Because we have saved them to the disk already. So we have the partition of both relation R and relation S. They will have different buckets, right? And they correspond to each other. For the ones with same bucket ID, they will have the same values for the attributes, right? Then we can do the joins between them. So for the joins, we can also do actually in a very similar framework or similar architecture. We can design another hash function for the joins. Let's assume we have partition for R and S already. Then we can load both R and S into the memory, right? Let's assume we load one buffer for relation R. The R is a bucket for relation R. At the same time, we can also load the bucket from relation S with ID I, right? They have the same ID, right? So we can know they have the same value for the attributes. So we can load the I's bucket of both R and S. Then we can match them together. The way we do the matching actually is using another hash function. So we can hash this the input buffer according to H2. H2 is another hash function which is different from H we used before. So this H2 will assign the input buffer of the tuples to the corresponding tuple in the bucket of Si actually. If they have the same manner, we will generate the output and also write the result to the disk again. So we scan matching partition of S and also search for the matches between them with this H2 hash function. So in this way, we can do both the partition as well as the matching with a very similar framework. So for this kind of algorithm, we have some requirements. If you still remember, right, we need to ensure the mean BR and BS is no greater than M squared. So in the next page, we also show you the summarization of these different operators based on two-parse algorithm according to the hashings. So we show you how to do the operator both gamma as well as delta, right, for both grouping as well as duplicate elimination. With this algorithm, we have some requirements for M, right? M is larger than the square root of B, and the cost will be about 3 BR of the relation R, right? And we didn't show you with these binary operators, but we do the joins for you, right? We have different versions of the joins. For the one with the partition hash joins, we will have requirements for M to be larger than the mean of BR and BS, the square root. And the disk I/O will be about 3 BR plus 3 BS. You can compare its cost versus the conventional two-parse algorithm. This one will be much smaller because for the conventional two-parse algorithm, this cost will be about 5 BR and plus 5 BS for joins. However, here if we use the hashings, the cost will be lower down because for the conventional two-parse algorithm, we have to do the sortings inside the inputs loaded into the memory. However, here we don't do the sorting anymore. We just do the hashing directly. The cost has been lowered down to 3 BR plus 3 BS. And you can compare this cost with the one-parse algorithm as well as conventional two-parse algorithms to see the requirements for M as well as disk I/O costs. So you can have an understanding for these different operators implemented with these 3 different versions of the algorithms. Alright, so in the next page, we will show you how to implement different operators with another algorithm based on the indexing actually. And we will show how it works and what are the costs for this kind of new algorithm.